Hello! Today we're looking at a brand new topic called polar coordinates. But the question is, what are they? Let's find out. The first thing we probably want to talk about is our understanding of what the word coordinates already means. When you say the word coordinates, you're probably often thinking of what we call Cartesian coordinates, x's and y's, and they're pretty cool. They allow us to draw various graphs, and if you're sticking to graphs of the form y equals, we already know from the functions chapter that restricts us to graphs that have a many-to-one mapping or a one-to-one mapping. Of course, you can extend beyond that if you want more crazy graphs by just doing some operations to the y as well as the x. Like for instance, we can start having things like a circle, but then you're already starting to have equations that are of the form of things such as x squared plus y squared and some other stuff. And then if you want to go even more crazy than that, well, that's where we start encountering some difficulties. Let's say I want a graph that looks like a spiral. Let's say something that looks like this. That's pretty cool, right? And funny enough, you can draw these graphs using Cartesian coordinates. But unfortunately, the graph, or the equation I should say, starts to look a bit complicated. The equation for this graph, for instance, is tan of the square root of x squared plus y squared equals y over x. That's not very nice to deal with, particularly if you're then having to do some other maths with that equation afterwards. So that's where polar coordinates come in. Polar coordinates are an alternative way of defining where we are on a graph that will make it easier to represent certain graphs in a much nicer way when we're looking at an equation. But how are we going to do this? Well, we could start by taking a look at some axes and a point, and of course we're already aware that Cartesian coordinates define the position of a point based on how far away it is, left and right, from the origin, which is our x-coordinate, and then also how far away it is up and down from the origin, which is defined as its y-coordinate. But polar coordinates are going to do things a little differently. We're going to use a different set of variables to define the position of our point. And we're also going to give some things some different names. For instance, for a start, we're going to rename the origin, the point that was always 0, 0 before, as the pole. So actually, it's worth pointing out that that's where the name polar coordinates comes from. Pole, polar. You can already see what I mean. Then once we've defined what the pole is, you can then measure how far away the point is away from the pole. And we are going to define that distance as r, the variable r. And then we're also going to define the part of the x-axis where the positive values lie, in other words the positive x-axis, as the initial line. That then means we can then measure how much we have to rotate around from the initial line to get to our particular point. And we're going to define that measurement as theta. Theta is measured anti-clockwise from the initial line, and it's also worth pointing out theta is always measured in radians. The knock-on impact of this is that the initial line is sometimes alternatively referred to as the line theta equals 0, because if you're already on the initial line, you don't have to do any rotating to get to that point from the initial line. So these are the two variables that define polar coordinates, and at this stage, if you're feeling that these things are a bit familiar, if you've studied complex numbers, that's for good reason. And it's ultimately the reason why we sometimes refer to modulus argument form of a complex number as polar form, because we are reusing those same letters, r and theta, to effectively measure very, very similar things as to what they're measuring here in polar coordinates too. However, there are some additional things we need to be aware of that we could call conventions, if you will. I'm calling them conventions rather than rules because there are times when we might choose to deviate away from them. Rather than them being unbreakable rules that we can never go away from, these are things that we just prefer to do a lot of the time because it makes intuitive sense to do so. For instance, most of the time we say that r is a value greater or equal to 0 because we measure r as a distance away from the pole. The reason that makes things nicer is because if, for instance, we're talking about a point that's got a theta value of pi over 2, that means if we're rotating anti-clockwise from the initial line, we'd be expecting to end up on a place somewhere along what used to be the positive y-axis. But that's assuming that r is greater or equal to 0. In other words, we're not having to really worry about direction, you just travel forwards. Whereas if r could be a negative number, that's starting to reintroduce those issues with vector quantities where it matters if we're going forwards or backwards. And therefore it means that if we're at theta equals pi over 2, despite in theory having to be on the positive y-axis, if you have a negative r value, it means you could end up being somewhere down here. And that's weird because that's not exactly where you'd be expecting to find a point that's got a coordinate of theta equals pi over 2. But that's not very nice because we generally prefer to think of polar coordinates as this thing that's travelling around rather than also having to think backwards and forwards in relation to the pole. And then the other convention that we often stick to is we often choose to make theta only be values between 0 and 2 pi. Now that is definitely of the two conventions the one that is even more loosely followed, and that's just because most of the time we're only sticking to 0 to 2 pi, just because if you're talking about a graph that goes between 0 and 2 pi, if you extend beyond there, a lot of graphs will just be repeating the same points again, therefore making it pointless to go beyond 2 pi. But sometimes there are graphs that will lead to different points if you do extend beyond 2 pi, so therefore that's a reason why we might not want to stick to just between 0 to 2 pi. Generally, most exam questions should make it clear what boundaries they are looking at, so basically do pay attention to the wording in the question or anything defined in the algebra, because that will affect potentially how you approach it. The other aspect to all of this is we have mentioned the word polar coordinates, and that's because we do write polar coordinates as coordinates. So that means writing them with the brackets and the commas like normal, except instead of the first value inside the brackets being x and the second one being y, we write it so the first number referenced inside the brackets is the value of r, and the second value referenced is the value of theta. Okay, so now we know what polar coordinates are. Actually, why are they more helpful than normal Cartesian coordinates? Well, as I said, if we're looking at any graphs that are to do with things going around rather than just up and down, then polar coordinates are a much more efficient way of expressing the equation. For instance, if we have a circle with a radius of 3, then all of a sudden the equation for that becomes a lot simpler than before. Not because we couldn't do it before, but because now the equation is just going to be r equals 3, because all the points on a circle with a centre of 0, 0, a distance of 3 away from the origin, are going to be a distance of 3 away from the pole, so therefore r, being a measurement of the distance from the pole, would just be the constant value of 3. And then you might remember that spiral graph we looked at earlier. Well, technically the equation for that in polar coordinates would have been r squared equals theta squared, but that's only because we had a double spiral, and I was only doing a double spiral due to restrictions that we have when we're doing Cartesian coordinates. In reality, if you want a more simple graph like a single spiral, that's actually got a very easy equation of r equals theta when we're looking at polar coordinates. The graph looks like this because it's saying as you rotate away from the initial line, you are therefore of course increasing the value of theta, but if r is equal to theta, that means that r is increasing as well, which means as we rotate around, we're getting further and further away from the pole. This is also a good prime example of situations where we sometimes might want to not just stick to being between 0 and 2 pi for our values of theta. Because if we extend beyond 2 pi, of course we're going to be getting different points to the ones we had before. Okay, there you go. That is an introduction to polar coordinates, and we're going to be doing a lot more things with them, but for now that's at least just explaining what they are and how they're defined, and I'll see you in a future video to actually look at doing some maths with them. Okay then, goodbye.